In this video, we will be looking at the effect of the k-value on your different base functions. So your k-value is something that affects horizontal transformations, and anything horizontal is inside the bracket. So your k-value is within the function and it's attached to x by multiplication. Now, the k-value is something new. You haven't seen it in grade 10. So if you want to plug some of these functions into Desmos to visually see it before we get into graphing, you're more than welcome to do that. Now, I will tell you what the k-value does. So the k-value, like I said, is horizontal, and it will do your horizontal stretches and compressions. But the k-value is a little opposite to what you might think. So if the absolute value of k is greater than 1, you might think that it's a horizontal stretch, when in fact it is a horizontal compression. And it will be by a factor of the reciprocal of k. So if your k value is 4, let's say, it is a horizontal compression by 1/4 because you're compressing. So you want the factor to be less than 1. And then if the absolute value of k is less than 1, then you actually have a horizontal stretch. And again, by a factor of the reciprocal. So let's say your k value is 1/3. The actual stretch factor is 3. Now, if your k value is negative, it's going to be a reflection, just like when your a value was negative. But when your a value was negative, it was a reflection over the x-axis. When the k value is negative, it is a reflection over the y-axis because it is a horizontal transformation. So if your k value is greater than 0, so if it's positive, it might be a stretch compression, but it is not a reflection. If it is less than 0, so if it's negative, there is a reflection over the y-axis. So all of these horizontal transformations, they are inside the function, inside the bracket, and they affect your x coordinates. So let's go ahead and start off with communicating transformations and setting up equations. So the first function we have is cos x, and the equation is f at negative x. So think again about your function notation. Negative x is inside the bracket, so I'm going to replace x with negative x. So my transformed function g of x, but you can use any letter, is going to be cos negative x. And because it's within the bracket, that's your clue that it's horizontal. So now, because the value is negative, I know there is a reflection over the y-axis. And because the absolute value is 1, there's no stretch and no compression. All right, let's try the next one. For the next one, we have a parabola, and inside the bracket, we have 3/4x. So I'm going to replace the x in x squared with 3/4x. And I'm going to put that in brackets and then apply the exponent. So for the horizontal stuff, the function applies to all of those transformations. So here, 3/4 is less than 1, which you might think is a compression because that's how we saw it with the vertical, but it's actually going to be the reciprocal. The reciprocal of this is 4/3, and that tells you that it is a stretch. So we have a horizontal stretch by a factor of 4/3. And if you don't believe me, you can go onto Desmos and plug that in and see what happens horizontally. Don't look at it as a vertical transformation, look at it horizontally. So how did the distance from the y-axis change? Was your parabola stretched horizontally or compressed and got closer to the y-axis? All right, so I want you to pause the video here and try the square root function. Write the equation and write the transformations. Okay, so for your equation, hopefully you have the square root of negative 5x. So that negative 5 is under the square root. And you might look at this and say, well, this isn't going to exist because I can't square root a negative number. You're right, you can't. But if x was a negative value, a negative times a negative is positive, and then I can square root that. So that problem is fixed when you state the domain later on. Now the transformations, we have a reflection over the y-axis, and we have a horizontal, so k is greater than 1, which means it's actually a compression. So horizontal compression by a factor of the reciprocal, which is 1 over 5. And I don't care about the negative. The negative told me the reflection piece. All right, last one. Pause the video again and try it out with the rational expression. It's going to look a little ugly, but that's okay. You don't have to simplify it or make it look nice. So your equation should be 1 over 7 over 2x, and you can keep it like that. Yes, it can get simplified, but this is fine for now. And our transformation is a horizontal compression again by a factor of 2 over 7. So if you just take the reciprocal of k, then you can look at it as a stretch or a compression. And the reason we know that we have to do the opposite is if you go into Desmos and visually see it. Okay, let's actually try some graphing now. And the first one is our rational function. So I'm going to start off by graphing the base function on my grid. So hopefully you're pretty efficient at it. And remember, the rational does have asymptotes, so maybe you want to draw the dotted line on the x and y axis so that you remember you can't touch or pass it. And I'm going to label this as f at x. Okay. Now let's write the equation for this function. So we have f at negative 1 over 4x, so that would be 1 over negative 1 over 4x. So for our transformations, we have two. We have the reflection over the y-axis, and if I take the reciprocal, I get 4, so we have a horizontal stretch by a factor of 4. Now, just like with the a value, you can do this all in one step, or you can do it in 2 steps where you reflect over the y-axis first and then stretch everything. I'm going to do it in 2 steps in this example, but typically I will do it all in 1 step. And something I want you to note, and we will see it when we get to our graph, is that horizontal affects your x coordinate. So when I'm stretching this, I'm going to apply the stretch to the x coordinates because I'm trying to move away horizontally from that y-axis. So let's try our reflection first. So for the reflection, I'm going to take all of these coordinates and I'm reflecting them over the y-axis, which means this little curved arm will now end up here when it's reflected, and this bottom one will end up on the right. So this used to be the right arm, and this used to be the left one. And I will label this as f at negative x, because all that we've done is reflected it. And notice what happened to the x value. So this x value used to be negative 0.5, or sorry, positive 0.5. Now it's negative 0.5. This one's 1, now it's negative 1. This one's negative 1, now it's positive 1. So it's the x coordinates that are being reflected. Now let's try that stretch of 4 from the blue rational expression here. So if I take this point that's at 0.5 units away from the y-axis. I want to quadruple that distance. So if I multiply that 0.5 by 4, I'll get to 2. So if I want to quadruple the distance, I'm going to be at -2 now. So I took the x coordinate and I multiplied it by 4. When I take this value, I'm 1 unit away. I should now be 4 units away because -1 times 4 is -4, so I end up right here. And then this point is at -2. -2 times 4 is -8. So I have quadrupled that distance. And then I will connect my dots and put arrows and then go towards my asymptotes. So if you look at this horizontally, this arm here has been stretched away from the y-axis. So it's a horizontal transformation and it's affecting the x-coordinate. Now I'll do the exact same thing on the other blue arm. So this point was at 0.5, now it's at 2 on the x-coordinate. This was at 1, now it's at 4. The one that's at 2 is now at 8. And notice that the y-coordinates did not change. I just stretched it away horizontally. And now I'll label this as g of x. Okay, and again, with these stretches, compressions, reflections, the asymptotes did not move. So now I will just write my domain, which is the same as the base function, which is just x cannot equal 0. And my range is that y cannot equal 0. And that's it. Let's try another one. So the next one we have is the square root function. So I'm going to start off by graphing my square root function with its key points. And I will label it as f at x. Now my equation g of x, instead of the x under the square root, I'm going to write 2x. And in terms of transformations, if I take the reciprocal of that k value of 2, it's a half. And that means I actually have a horizontal compression by a factor of 1/2. So now if I go to my graph, I'm going to take all of these x-coordinates and I'm going to bring them in halfway towards the y-axis. That's what makes it horizontal. So this first point that's on the origin, that's not going anywhere. But this point here, that is 1 unit away from the y-axis, it will now be half a unit away. This point that's 4 units away, I'm going to cut that distance in half. So 4 times a half is 2. So that point came in. The point that's at 9, 9 times a half is 4.5. Now notice the y-coordinate is still 3, so the point that was 9, 3 is now 4.5, 3. Sorry, 4.5 is here. And now we can connect our dots, and we can call this g of x. And there we go. Okay. So for c, we have the exponential function 2 to the power of x. I want you to pause the video, write the equation, write the transformation, draw your base function, and do the transformation you have to do. So pause the video, try it, then come back to check your work. All right, so for your equation, it's going to look a little weird here because you have a fraction in your exponent, but this will be 2 to the power of 1 over 3x, which means we have a horizontal stretch by a factor of 3. So I drew in our typical 2 to the x function, and now I'm going to stretch everything horizontally. So again, the x coordinates are going to get affected here. So the y-intercept's not going anywhere because it's on the y-axis, but the point that's 1 unit away horizontally will now be 3 units away. I'm stretching it away. The point that's 2 units away, 2 times 3 is 6, so it's now going to be at 6, 4, but the y-coordinate stays. Then the one that's at 3, 8 will now be at 9, 8 because I tripled the distance horizontally. And then I'll do the same to the other 2 points that I have. At negative 1.5, I'm now going to be at negative 3.5. And then negative 2.25 will now be at negative 6.25. And then we can connect to get this horizontally stretched exponential function. Now, when you look at this, you might say, well, that kind of just looks like you also took the exponential function and vertically compressed it, and you would be right. With your vertical and horizontal stretches and compressions, you can interchange between the two, and you can actually write one in terms of the other, but that's not for now. All right, let's go to our last one, which is our sinusoidal function, sine x. So again, I want you to pause the video and try it out on your own and see what happens to your sine function when you apply these transformations. Now, for your equation, you should have sine of negative 2x, which means you're reflecting over the y-axis, and a horizontal compression by a factor of 1/2. Now, if you look at my grid here, I have drawn our typical sine function, but there's space on the left. So I'm actually going to continue this wave and see where it takes me. And I know every key point occurs every 90 degrees. So if I follow the wave, when I go to the left at negative 90 degrees, I should be down here at the minimum. So I'm just going to continue it, because if you have this full grid, the full grid should be filled with your function. All right. So if you want to do both of the transformations at the same time, you can, or you can do them step by step. If you do it step by step, you want to reflect your sinusoidal function first, which means this little piece will end up here, and this piece here on the right will end up on the left. And you'll still have the same wave function, but reflect it. And then you can compress all of your points in towards your y-axis and bring them in halfway. Or you can do it all at once. And I'm going to show you how to do it all at once. Because we know the horizontal affects the x-coordinate, I'm just going to take all of these x-coordinates and multiply them by negative 1/2. Now I know your k value is negative 2, but you're compressing by 1/2. So I'm going to make a little note here. Multiply x values by what the transformations are. Negative for the reflection, 1/2 for the compression. So the point that's at the origin, that's not going anywhere. The point that is at 90, 1, it's now going to be half the distance. Originally, it's 90 degrees away. It's now going to be 45 degrees away, but on the negative side because of the reflection. So it's actually going to end up on the left side. The point that's at 180, 0, right over here. When I multiply 180, which is the x-coordinate, by negative 1/2, I get negative 90. So that gets reflected and compressed right over here. The point that is at 270, when I multiply it by negative 1/2, I'm going to end up with negative 135. So that will take me here. Then the 360 times negative 1/2 will take me to negative 180. So that right side on the positive x-axis will become this. Once you have a full cycle, you can just continue your pattern. You don't have to go to this left side and multiply all of these values by negative 1/2. You can if you want to, but the minute you have this cycle, you can continue the pattern. And if you look at this new pattern, every key point doesn't occur every 90 degrees anymore. It occurs every 45 degrees. So I'm just going to continue it. To the right, I'm going to go down to my minimum and then start my wave. So it will look something like this, every 45 degrees, not missing a point. And then I can connect. So it looks something like that. And then on the left, from that negative 180, I'm going to go up to the maximum to make it look like it's flowing nicely. And there we go. This is your g of x. Now what you might notice is that the cycle is shortened, so the period is actually now 180 degrees instead of that 360, and that's because we compressed it. So the period that used to be 360 is now half of what it used to be. Now let's go ahead and do our domain, which is just x is an element of all real numbers. And the range, because we didn't do anything vertically, the range is still from -1 to +1. And there you go. That is your k value. So the k is horizontal. And I am going to make a little note here that all horizontal affects the x coordinate. So when we had the right-left movements, that affected the x coordinate. Now when we have the horizontal stretches, compressions, reflections, you're multiplying x by that factor to do the transformation.